Humans have long conjured up images of what life might be like on distant planets, and when the search for exoplanets entered its golden era, interest in Earth 2.0, our planet's twin, circling within the habitable zone of its star, increased. However, searches have so far come up empty, forcing researchers to employ some creative thinking to locate another possible home for life in the universe. That query can now be resolved thanks to the James Webb Space Telescope. The most powerful telescope in the world will provide fresh resources to answer the age-old question of whether or not there is life outside of Earth. Join us as we explore James Webb's terrifying discovery of city lights that changes everything. The only life we are aware of so far is on Earth. People have questioned if there is life in the universe since the dawn of civilization. The search for extraterrestrial intelligence SETI project was started in 1984 by American astronomers Jill Tarter and Thomas Pearson to conduct such interstellar searches. The nonprofit organization's goal is to collect radio transmissions from space. Because radio waves are less scattered or absorbed than other types of radiation, they can travel farther and are therefore more likely to be picked up by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. However, no confirmed alien signal has been picked up in 30 years. After that, the search was helped by the successful deployment of the James Webb Space Telescope JWST, the largest telescope in the world, which is floating about 1 million miles from Earth and equipped with extremely sensitive detectors, will study a variety of distant, undiscovered planets orbiting far-off stars. Other than the planets in our solar system, no other planets were recognized 20 years ago, but more than 4,000 more planets, sometimes known as exoplanets, have since been found orbiting other stars. According to NASA, there could be trillions of exoplanets in the universe. Extraterrestrial plant life may provide the earliest indications of life outside of our solar system. While traveling, Galileo's spacecraft turned its instruments back toward Earth and detected the definite sign of the presence of plants. The Vegetation Red Edge VRE biosignature, a combination of red and infrared light reflected by plants, was picked up by the device. If there is an Earth-like planet covered in jungle, for example, it should have a strong VRE signal that should be simple to detect. The JWST will measure the VRE of distant Earth-like planets in the habitable zone around stars. The makeup of the exoplanet atmospheres may contain significant indicators of life. The JWST may be able to detect sunlight passing through an exoplanet's atmosphere when it crosses the face of its star. The missing wavelengths in the light would subsequently be found using spectroscopy. The atmosphere's atoms and molecules absorb particular wavelengths, leaving a distinct fingerprint that the JWST can detect. In this approach, the atmosphere's makeup may be discovered and the potential for life can be deduced. If Earth-sized planets with atmospheres like our own were discovered with a predominance of oxygen, nitrogen, and carbon dioxide, those planets would probably be able to sustain life. And it could be possible to spot technological life by checking for the presence of substances that don't happen to occur normally. Chlorofluorocarbons, CFCs, which were produced for use in cleaning products and refrigeration, would likely be visible to aliens observing Earth's atmosphere from a distance. CFCs in planetary atmospheres would be a telltale sign of a civilization if the JWST discovered them. In fact, life on exoplanets might not resemble life on Earth at all. Even earthly life, such as extremophile species, can occasionally appear foreign. This is a group of organisms, primarily bacteria, that can survive in conditions that would make it impossible for other living things to survive. Some of them can tolerate temperatures as high as 250 degrees Fahrenheit. Others can endure temperatures as low as -4 degrees Fahrenheit. Others exist on Earth in locations where we would not anticipate finding any life at all, including some that live in strong acids with pH levels below 3. However, it would be wise to start looking at Earth-like planets first, since they are more likely to host life than planets with extreme temperatures or acidic environments. Prime candidates may orbit a stable star and have temperatures that permit liquid water to exist on their surfaces. Our Sun is characterized as a yellow G-type star, but in our universe, these stars are less frequent and typically have shorter lives. Planets revolving around red dwarf stars, which are more prevalent and have a lower luminosity and temperature than the Sun, may be a more likely subject of study. Because of the substantially longer lifespans of these stars, there is more time for the emergence of life and for evolution to produce complex life forms. JWST's initial mission will examine the TRAPPIST-1 planetary system around 40 light-years from Earth. It comprises 7 rocky planets the size of Earth around a peaceful red dwarf star. In the so-called habitable zone, 3 of the rocky planets could have liquid water on their surfaces. Despite having a considerably smaller and cooler mass than our Sun, the TRAPPIST-1 star, because of its planet's tight orbit, emits light that is comparable to that of Earth. Proxima Centauri, a red dwarf star that is 4.25 light-years away from the Sun and our closest star, offers us the best opportunity of observing city lights outside of the solar system. A planet must be 20 times closer to Proxima's furnace than the Earth is to the Sun in order for it to support life based on liquid water, because this star is approximately 600 times fainter than the Sun. In this habitable zone, astronomers identified a planet in August 2016 that weighed 1.3 Earth masses. The fact that Proxima b orbits its dim red dwarf star Proxima Centauri at a distance of only 4.6 million miles raises the possibility that it is a lifeless, airless planet. In contrast, Earth is 93 million kilometers from the Sun. Proxima b is in a tight orbit that provides enough sunlight for temperatures similar to those on Earth and liquid water, but it also exposes the planet to strong solar winds that can completely destroy its atmosphere. Proxima b is believed to be tidally locked, showing the same side to the star at all times as the Moon does in relation to Earth as a result of its close proximity to the star. There is a permanent day side and a permanent night side on Proxima b. Sadly, models indicate that tidally locked planets' atmospheres may be vulnerable to rapid collapse as volatile gases freeze out on the night side. However, volcanic activity can also replenish atmospheres, and on planets with powerful magnetic fields, these atmospheres are less likely to escape. We are unable to even speculate about Proxima b's likelihood of having an atmosphere because we have no knowledge of the planet's volcanic activity or magnetic field strength. But we're desperate to know, since an atmosphere implies the existence of seas, and the two combined imply the existence of life. If a sophisticated civilization already exists on Proxima b, its day side may be covered with solar cells to provide electricity that would light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The JWST enters the picture here. The infrared heat signature on Proxima b holds the key to detecting the atmosphere of the planet. Additionally, Hubble's successor has a strong affinity for the infrared region of the spectrum, so the James Webb Space Telescope might be able to see city lights on Proxima b's night side permanently. Webb could detect artificial illumination as long as it was restricted to a frequency band that is 1,000 times narrower than the starlight, even if it were as weak as what our civilization currently uses on the night side of Earth. Based on its distinctive spectral edge in reflecting starlight, Proxima b's day side is covered in solar panels to a significant extent. There is no difference between day and night as Proxima b orbits its star. The temperature is hot during the day and cools at night. However, because an atmosphere and ocean transfer heat, the temperature difference between day and night depend on whether the planet is made up entirely of bare rock or not. In other words, if there is no atmosphere, the temperature differential between Proxima b's day side and its night side will be greater. In fact, we can compute the precise amount of blackbody radiation that should be there because the day side will re-emit all the energy it gets from Proxima Centauri as a black body. On the other hand, the night side will resemble a frozen version of hell. We can assume the existence of an atmosphere if there is a less dramatic temperature differential between day and night. Conveniently, the JWST will quickly complete its orbit around Proxima b, taking only 11.2 Earth days to measure the infrared radiation from both of its faces. The next stage will be to determine the composition of Proxima b's atmosphere, assuming that it does have one. In particular, we'll want to keep an eye out for substances like oxygen, water vapor, and methane, because they might point to the presence of habitable conditions, if not living organisms. However, to do this, we must capture starlight as it reflects off or passes through the planet's atmosphere, which is a very challenging task. However, because Webb was not designed to search for extraterrestrial life, the telescope can only closely analyze a few of the closest potentially habitable worlds. Additionally, it is restricted to monitoring changes in water vapor, methane, and carbon dioxide concentrations in the atmosphere. Even while some mixes of these gases may be suggestive of life, Webb is unable to detect the presence of unbonded oxygen, which is the strongest indicator of life. The extremely large telescope, which is anticipated to start operations in the middle of the 2020s, is one of the upcoming ground-based observatories that will be able to perform a full atmospheric analysis. The JWST may be able to detect a few compounds, including ozone. A cutting-edge concept for the future, even more potent space telescopes includes ideas to block the glaring brightness of a planet's host star in order to expose starlight reflected back from the planet. To better view something in the distance, think of doing something akin to blocking the sun with your hand. Small interior masks or big exterior umbrella-shaped spacecraft could be used in future space telescopes to accomplish this. Studying light reflecting off a planet is significantly simpler after the starlight is obstructed. Meet humans. Let us know what you think in the comments section below.